All right, so um, I'm going to apologize. There's a bit of a distractor in this problem that you need for part B, but not for part A. So I'm just going to actually take this fact here and sort of let you just kind of take it out of the way. And this is velocity. Oops, cross this out. There's that. And this radius part, it is useful, but I'm going to write it down here because that's where we actually need this fact. Okay. So let's be clear on what's happening. What's happening is I'm launching a charge this way that has a mass of 0.05 kilograms, 0.005, sorry, and a speed of 10 meters per second. And what's happening is that right here, its speed goes to 0, okay? And it's because of this positively charged sphere and the fact that this little charge here is positive and there is a repulsive force. Okay. That's the idea. So what we're going to do is actually use energy considerations because that's the hint we're given. So what's happening in this problem is that we have kinetic energy being entirely converted into E electrical. And what we're going to do is we're going to set up that formula for electrical energy. Now, it turns out this is a very specific type of electrical energy, the electrical energy put out by a sphere. So what I'm going to do is I'm actually going to write an energy equation based on these two here for a conducting sphere and the charge that is acting on. So this energy is stored between the two charges. So we're going to have K, Q of the conductor, Q of the little charge that's moving towards it, divided by R. So that's the energy where I've taken this V and I've substituted my expression for potential difference right there, or voltage right there. Now, what I'm going to do is I'm going to take my kinetic energy and convert it entirely into electrical energy with none dissipated. And now, just like my energy bar graphs, I'm going to have 1/2 mv squared equals k, q of the conductor, q of the moving charge, divided by the distance that separates them. And it is actually this distance, this radius. So when I say radius, I mean, what I really mean is that the potential all around here at this radius is going to be what I calculate here, but I'm focusing on this particular point here, okay, a distance from the center. So yes, often we do use the term radius and distance interchangeably. Now, in this particular case, we're going to go ahead and put in our numbers. So we have 1/2. M is 0.005. V is 10 meters per second squared, equals 9 times 10 to the negative 9th. Q of the conductor is 2 microcoulombs. When I'm dealing with energy, I always use my full numbers. And then the Q of the charge that's interacting with this conductor is 4 times 10 to the negative 6. And the distance separating them is going to be the unknown that we're solving for. So let's do a little bit of algebra and we'll solve. So we're going to end up getting here, just, so 5 times 0, 0.005 times So that gives me 0.25 here. And that's going to equal, we got quite a bit here. And this is 10 to the positive 9th. I apologize for that. So that's going to be 2 times 18, 2 times 9 is 18 times 4, or 9 times 8 is 72 times 10 to the negative 3 over r. You don't need to do it this way. I'm just kind of solving this the way I can. So then when I isolate, I'm going to get r is 0.072 divided by 0.25. So when I actually solve that, I'm getting a distance of 0.288 meters from the center. So that's where the moving charge is forced to a stop because of the work done on it by the sphere, or if you'd like, it's because the kinetic energy of its motion has been converted entirely into electrical potential energy. Now, the capacitance of the conductor. We know the charge on the conductor is 2 microcoulombs. And now let's get the voltage at its surface. The voltage is going to be K Q over R. So I'll also write this as 2 microcoulombs, and we'll see. So we got 9 times 10 to the 9th times 2 times 10 to the negative 6th divided by its radius, which is 0.5. So the capacitance actually ends up being Q over V. That's going to be 2 times 10 to the negative 6th divided by 9 times 10 to the 9th, 2 times 10 to the negative 6th. Now that little 0.5 on the bottom, that actually comes up top. This is how fractions work with division. Okay, so don't forget that fact. So now I'm going to end up getting these cancel. And I'm going to get 0.5 divided by 9 times 10 to the 9th. And that's going to give me 4.44 times 10 to the negative 11th farads. That may not be a bad number. All right, so that is the capacitance conductor problem number 2.